Yes, sir. You can start the session, sir.
Yes, ma'am. Thank you,
I
ma'am.
made you host, sir.
Yes, ma'am. Good morning, everyone. So let's do some basic problems on survival. Same radial acceleration and tangential acceleration yesterday. So speed, I can say tangential acceleration is zero because when you constant speed, there is no change in tangential speed. So tangential acceleration is zero. But not a radial acceleration because radial acceleration is responsive for its turn. Even if the speed is not changing, there is change in the vector. There is a change in direction of the motion of the particle. So there is a radial acceleration. That radial acceleration, but the delta Vy, let us see how do we find radial acceleration. I need delta V for that. How do I find delta V? V2 minus V1. V2 is V1. V2 minus V1. V2 is the same. Can you find the delta V now?
So your voice is not audible.
Oh, sorry, ma'am. It's audible now, ma'am.
Yes, sir.
Right.
Now
Thank you,
it's
ma'am.
me.
All right. V2, see, all I'm doing is I'm finding out the change in velocity. Can you find the change in velocity delta V? Is V2 minus V1, V2 plus or minus V1. So I reverse V1 and add it to V2. So I get resultant to be somewhere here, angle bisector, which is V naught root 2 at an angle of 45 degrees with a vertical or with a horizontal because angle between them is 90 degrees. So I didn't tell you the angle, right? This has rotated to an angle of pi by 2. The particle has gone from 0 to pi by 2. All right. Now, how much time does it take from here to here? Length, distance traveled is. All right. Tell me what's the change in velocity? V root 2. In time delta t, let's say. So acceleration would be V root 2 by delta t is my acceleration, average acceleration. But what is delta t now? I need to substitute delta t as well. So delta t would be this length divided by speed. How much is this length? If radius is r into pi by 2 is the length of that. By speed is v naught. So delta t is pi r by 2 by v naught. Do you understand this? Do you understand delta t? Delta v you have understood. It is v2 minus v1. That's fine. Delta v by delta t is my average acceleration, whereas delta t is pi r by 2 by v naught. Is it okay? So my average acceleration now is v root 2 by pi r by 2 by v naught. So I'll have 2 goes on top. V naught square 2 root 2 by pi r is my average acceleration. This is in time pi r by 2 by v naught. Why is it time pi r by 2 by v naught? Because distance r is pi r by 2. Length of the arc is pi r by 2 or r theta pi r by 2 by speed, constant speed is v naught. So it's going with constant speed. So time would be distance by speed is the time taken. In that time, change in velocity is magnitude of change in velocity is v naught root 2 in this direction. So my average acceleration is in this direction of magnitude this much. All right. Now let us generalize this. Let us say it has moved an angle of theta at so an angle of theta instead of pi by 2. And let us generalize the result. When it is moved through an angle of theta, can you tell me what is delta v in that case? I'll tell you delta t. Can you tell me what is delta v? v2 minus v1. So v2 is this way, v1 is this way. So resultant is somewhere here. I mean, this is minus v1. This is v2. Both of magnitude v0 and v0. So resultant is somewhere here. And what is the resultant now? If this angle is theta, this is if this is theta, this is 90 minus theta, and this is theta. Sorry, 90 minus theta again. So can you tell me the resultant of these two vectors? Equal vectors, equal in magnitude, two vectors equal in magnitude at an angle of one 180 minus theta. Angle between the two vectors is 180 minus theta. You have to tell me the resultant of these two vectors. Either you can use the resultant formula v1 square plus v2 square plus 2v1 v2 cos theta, where theta is pi minus theta here, alpha. Pi minus theta is the alpha here. Angle between two vectors is pi minus theta. If an angle rotated, so if a particle is gone through an angle of theta, angle between two vectors is pi minus theta. So that is one way you can do, or I can do V naught because I know the angle resultant is going to be along the angle bisector. This is 90 minus theta by 2. This is 90 minus theta by 2. V naught cos of 90 minus theta by 2. V naught cos of 90 minus theta by 2. So that would become 2 V naught sin theta by 2. By time taken. Do you all understand this? 2 V naught sin theta by 2 is the change in velocity, magnitude of the resultant or delta V.
No, sir.
Do you understand this? D2 V naught sin theta by 2?
No, sir. No, sir. No, sir.
No? Alright. See, I'll tell you. I'll have V naught square plus V naught square plus 2 V naught cos of pi minus theta under root is my delta V. Alright, which is the resultant of these two vectors, V naught and V naught at an angle of pi minus theta. Why am I taking pi minus theta? Because angle between them is pi minus theta. How do I know that? If this is theta, this angle is also theta. This total angle is pi. This angle between two vectors is pi minus theta. Alright, now so this becomes V naught 2 V naught squared plus 2 V naught square cos of pi minus. What is cos of pi minus theta? Can you simplify this and tell me? What do you get ultimately? This is one way of doing it. I'll show you
Minus
other
cos
way as well.
theta.
Other way is simpler, but you should know this way as well.
Sir, minus cos theta.
Sorry?
Minus cos theta, sir.
Yeah, minus cos theta. So that becomes 2 V naught square into 1 minus cos theta under root. Now tell me what is root of 1 minus cos theta? How can I write 1 minus cos theta as?
Sin theta, sir.
Sorry?
Sin theta.
What is 1 minus cos square theta?
Sin square theta, sir.
So what is 1 minus cos theta? No, that is not sin theta. 1 minus cos theta is not sin theta. I'm telling you what is 1 minus cos theta. 1 minus cos square is sin square. But what is 1 minus cos? You can write in terms of half angle, theta by 2. 2 sin square theta by 2.
Yes, sir. 2 sin squared by theta by 2, sir.
Right. So I can write 2 V naught sin theta by 2. That's what I got delta V as. That's what I was writing, right? Delta V is this much. Now, if delta V is this much, what is the acceleration, average acceleration? This by time. How much is the time taken? This length by speed. R theta by speed. R theta by speed V naught. So that becomes 2 V naught square sin theta by 2 by R theta is my average acceleration. Now look at this. If theta tends to 0, If theta tends to 0, I have got sine theta by 2 as, I can replace that with theta by 2. I can approximate that to theta by 2. So 2 V naught square theta by 2 by r theta. Theta gets cancelled, 2 gets cancelled. I'll have V naught square by r. That's what the centripetal acceleration is, right? We have seen the formula for centripetal acceleration to be V naught square by r. That's what we have derived V naught square by r centripetal acceleration for the case when the particle is moving with constant speed. But that is the case for general velocity as well. Whether the particle is going with constant speed or not, when I limit sine theta by theta to tends to 0, my centripetal acceleration is always V naught square by r. No matter what the tangential acceleration is, whether the particle speed is increasing or decreasing, at certain instant, when the speed is V naught, that instant, centripetal acceleration is V naught square by r. All right. But we have done using this method, right? Now I want to tell you a simpler method. And this is what you should know because we are going to apply this very often. This is V naught. This is minus V1. So resultant will be somewhere here. If this angle is theta, this angle is pi minus theta. So this half angle would be pi by 2 minus theta by 2. This would be pi by 2 minus theta by 2. So V naught cos of pi by 2 minus theta by 2 plus V naught cos of pi by 2 minus theta by 2 is a resultant. So 2 V naught cos of pi by 2 minus theta by 2. What is cos of pi by 2 minus theta? Theta by 2?
Sine pi by 2. Sine
Sin
theta
theta
by
by
2.
2. So that's what my resultant is, right? Delta V is this. So which is simpler? This is simpler. Whenever you have two equal vectors, take the resultant to be along the angle bisector, take the component of individual vector along the angle bisector and add them. All right. I hope you have understood. Now listen. Now I've got the centripetal acceleration to be in this direction, AC. And let's say AT in this case is 0. So net acceleration would be resultant of AT and AC, which is along AC. In circular motion, you will definitely have AC. AT may or may not be 0. All right, AT could be 0 or non-zero. But you will definitely have AC. AC will never be 0 in a circular motion. It is 0 only when the particle is at rest. But the moment the particle is moving along a circle, you will definitely have a centripetal acceleration because that is responsible for the change in direction. That is not responsible for the change in speed. For the change in speed, responsible is AT. For the change in direction, responsible is AC or AR, radial acceleration or centripetal acceleration. It's called centripetal because it's towards the center. It's called tangential because it's along the tangent. All right. Okay. Now let us enter into the dynamics of motion, dynamics of circular motion. We have been dealing with kinematics without talking about the forces. Now let's talk about the forces responsible for this acceleration resulting acceleration, centripetal acceleration and radial tangential acceleration. All right, but there is yet another thing. All right, first we'll talk about dynamics of circular motion, then we'll come back to radius of curvature of a path. I've got a. Is it visible? This is on horizontal table. Gravity is into the plane. I'm looking this from above. There is a smooth groove along which there is a particle moving with velocity v naught. If it's moving with velocity v naught and it is smooth, there is no relative motion. I mean, there is relative motion, but because it is smooth, friction is zero. If friction is zero, there is no tangential force on it. It's not vertical. It's not vertical circle. It's horizontal circle. All right. It's on table, horizontal table. It's moving like this on a horizontal table. Now, I told you the moment a particle is going in a circle, it will definitely have an acceleration. It may not have tangential acceleration, but it will definitely have centripetal acceleration, which is equal to v square by r. If radius is r, it is v square by r. V naught square by r is the centripetal acceleration. Now, look at this. There is no force tangentially, so this particle will go with constant speed along the circle. So no matter where the particle is, it will go with constant speed v naught. But because it has got is moving in a circle, it will have centripetal acceleration of v square by r. Now there is an acceleration, so there should be a force responsible for it. Which force is responsible for this turn? Normal reaction is responsible for this turn. So I can write normal reaction is equal to mass times centripetal acceleration. And there is no friction, F equal to 0, so AT equal to 0. In this case, AT is 0. But if there were friction, you would have AT as well. And what kind of friction you would have? Kinetic friction, because there is relative motion between the surface of the block and the groove should have relative velocity, because of which you would have kinetic friction. And that kinetic friction would result in retardation. Because friction is opposite to velocity in this direction, velocity is in this direction, friction would be in opposite direction. So this particle will retard eventually and stop somewhere. That time, in that case, you would have AT as well. But you would have AC definitely, but AT as well. The moment the particle stops, you have your AT and AC both will disappear and the particle's acceleration is zero. But the moment the particle is moving in a circle or in some curve other than straight line, it will definitely have AC. Because there is curvature, whenever there is curvature, there should be a center about which the particle is moving at that instant. It will have centripetal acceleration. All right. Now this is one normal reaction because of the ball. There is another normal reaction because of the ground surface. Let's say this is N1. N2 is out of the plane. Friction is anyway zero. I'll remove it. Now this N2 is equal to mg. So normal reaction because of the surface ground is mg. Normal reaction because of this groove, which is centripetal force, is equal to mv square by r. Why am I writing mv square by r? Force is equal to mass times acceleration. That's it. Newton's law, Newton's second law. All right, Kirchhoff's formulation of Newton's second law is force is equal to mass times acceleration. And here net force is equal to 0, N2 is equal to mg. So vertically there is no motion, but on the horizontal plane there is motion, which is because of centripetal acceleration. This particle is taking a turn because of centripetal acceleration. So I'll write force is equal to mass times acceleration. So N1 is equal to mass times v square by r, which is centripetal acceleration. All right. Is it clear?
No, sir.
Is the situation?
Sir,
Yes, yes, Vignesh.
ఇంటూ దగ్గర అర్థం కాదు.
N2 అర్థం కాలేదా? Right. See, I have a block. All right. This block is moving along a track on horizontal table. On horizontal table, it's moving along a track. So ground వల్ల normal reaction ఉంటుంది. That is N2. Now, because it's moving along a track, it will have some centripetal force, which is N1. So N2 is there, always there, because of mg. So mg is counterbalanced by N2. There is no vertical motion like this. There's only horizontal motion, motion in the horizontal plane, but there's no motion in the vertical direction. So N2 is equal to mg. N2 minus mg is equal to mass into acceleration, which is 0. So N2 minus mg is equal to 0. N2 is equal to mg.
Yes, sir.
All right. Okay, now let us understand another case. Where you calculate the centripetal acceleration and all right, situation is like this. Instead of a circle, perfect circle, let's say I've got some curve. Let's say there's a straight line, a particle is moving along a straight line with constant speed. Does it have centripetal acceleration? No, because there is no change in direction. If there is change in direction, it will have centripetal acceleration. Or when there is curvature, when there is change in curvature, whenever there is curvature of straight line is 0. It's not curved at all. If the curve is not curved, curvature is 0. If the curve is curved, it's not straight line, then it'll have curvature. So it'll definitely have centripetal acceleration. So whenever the particle is going along a curve which is not a straight line, all right, any path which is not a straight line will have a centripetal acceleration, and that will be centripetal acceleration about towards the center of a circle which is called as osculating circle. All right, it's not oscillating, it's osculating, which means that circle which just touches this curve. This curve is not a circle actually, but I can have a circle which is just touching this curve such that at that moment, at that instant, the particle can be assumed, no, particle not assumed, particle seems to go along this circle of radius, some let's say r. So centripetal acceleration will be v square by r, where r is called radius of curvature of the path, rc. So if I know acceleration, I can get the radius of curvature of the path, because radius of curvature of the path is nothing but v square by a naught. V square by RC is A naught. So I can just cross multiply. I'll get RC is equal to V square by A naught. So if I know the centripetal acceleration and velocity, tangential velocity, I can know the radius of curvature of the path. For a straight line, particle is going with constant speed V naught, AC equal to 0. So RC is equal to infinity. All not defined. AC is tending to 0, RC tends to infinity. AC tends to 0, RC tends to infinity. If AC equals 0, RC is not defined. Therefore, I told you radius of curvature for a straight line is not defined. It doesn't have curvature at all. So radius of curvature is not defined for straight line. But for some other curve, any other curve, if I have got velocity, tangential velocity, and the radial acceleration, I can get the centripetal. If I know the centripetal acceleration, I can get the radius of the oscillating circle, which is radius of curvature of the path at that instant, at that particular point of the curve. All right, now All right. Now let us say I've got a parabolic path. The particle is projected with velocity v naught at an angle theta. It goes under gravity in a parabolic path. I have to determine the radius of curvature at certain instant. So what do? I told you to determine the radius of curvature at certain instant, I need centripetal acceleration, radial acceleration. Once I know radial acceleration at the speed at that instant, I can write projected velocity v naught. I have to determine the radius of curvature of the path at the topmost point, where the speed is v naught cos theta. Why is the speed v naught cos theta? Because horizontal direction component of the speed is v naught cos theta, which remains constant in a parabolic path. So v naught cos theta remains constant. At the highest point, vertical velocity is 0, horizontal velocity is v naught cos theta. So speed at that instant is v naught cos theta tangential to the path. What is the centripetal acceleration at that instant? G. Right? The only acceleration present over there is G. So I got centripetal acceleration as G, tangential velocity as v naught cos theta. So radius of curvature of that path at that point is RC is v naught square cos square theta by G. So radius of that circle, which is oscillating circle, which is just touching the path in such that the particle seems to move in that circle at that instant. All right. There is yet another way of explaining this, but we'll talk about that later. It's very intuitive, but right now understand in this sense that radius of curvature of the oscillating circle is given by tangential speed by square by centripetal acceleration. Now let us say if I ask you what is the radius of curvature at the point of launch. So we'll have an oscillating circle somewhere here. Radius of curvature, tangential speed is v naught. G is vertically downwards. If this is theta, this is also theta. So my radial acceleration is now g cos theta. So centripetal acceleration is g cos theta, and tangential speed is v naught. So v naught square by g cos theta is my radius of curvature at the point of launch. So at any instant, if I have to find out, I just have to find the speed v, and the component of g perpendicular to the speed v. That is radial acceleration. All right, is that clear? How do you find radius of curvature at any instant? Or centripetal acceleration given the radius of curvature? Tangential speed by radius of curvature, tangential speed vt square by radius of curvature is centripetal acceleration. So radius of curvature is given by v naught square by centripetal acceleration. All right, we are just revolving about one formula, v square by r. AC is equal to v square by r. If the path is not circle, I can treat that to be circle at that instant of time, and the radius of curvature of that circle is called, radius of that circle is called radius of curvature of the path at that instant of time, or at that particular point. Do you want me to repeat this, or is it clear?
Can you repeat, sir?
Sorry,
Can you repeat it, sir?
your voice is not audible, Vignesh.
Can you repeat it, sir?
You want me to repeat it?
Yes, sir.
All right. Let's say I've got a path which is not circular. It's evident it's not circular. But at any point, I can draw a circle which is called an oscillating circle, which is a path, which is a circle about which the particle seems to go at that instant. Radius of that circle is called Radius of curvature of the path. So radius of curvature over here is, let's say, R1. Here it's say R2. How do I find the radius of curvature is? I know centripetal acceleration AC is V square by RC. So RC is equal to V square by AC. So given an acceleration and tangential speed, I can find radius of curvature. Radius of curvature has got nothing to do with tangential acceleration. It has got only to do with tangential speed and centripetal acceleration. So centripetal acceleration is AC. RC will be equal to V square by AC. Why? Because AC is equal to V square by R. How do you know this? We have just now derived. 2 minutes before, 5 minutes before, we have derived this. Centripetal acceleration is nothing but V square by R for a perfect circular motion. But even if it is not perfect circular, it has got some radius of curvature is going on changing. At that particular instant of time, this particle seems to rotate about a circle called oscillating circle, which has got a radius of curvature RC. I will find out RC by, if I know AC, I can find RC. If I know RC, I can find AC from this equation, from this formula. Let us find out radius of curvature for a particular particle which is projected in air with velocity v naught. So that will go in a parabolic path. Let's say this is theta. It's, let's say I have to find out the radius of curvature is the peak point, topmost point of the parabola, vertex of the parabola. So there will be a circle over here, oscillating circle, about which the particle seems to go at that instant of time. Radius of this is RC. Centripetal acceleration is G. And this is tangential speed is V naught cos theta. Why is it V naught cos theta? Because horizontal speed is V naught cos theta, which remains constant throughout. No matter where the particle is, its horizontal speed remains constant in projectile motion, if you remember. Because acceleration is only vertical, component of acceleration horizontally is zero. So there is no change in speed horizontally. Particle goes with constant speed horizontal, constant velocity horizontally. So I know G, I know AC, I know V tangential velocity. So RC would be V naught cos theta whole square by centripetal acceleration, which is G. Now let us have to find out this radius of curvature at the point of launch. I know tangential speed, which is V naught, V naught. So V naught square by centripetal acceleration is my radius of curvature. Now what is centripetal acceleration is what I have to find out. So centripetal acceleration is G downward is the acceleration due to gravity. Centripetal acceleration is G cos theta. Because if this is theta, this is theta, this is G cos theta. So A V square by G cos theta is my radius of curvature at point of launch. Whereas V naught square cos square theta by G is my radius of curvature at the vertex of the parabola. This is at the point of launch, this is at the vertex of the parabola. Now we have understood. Vignesh, any doubt now?
No, sir.
All right. Now look at the students. If I have got curvature, if I know radius of curvature, I can also talk about centripetal acceleration. Let's say particle is going along a track where here radius of curvature is bigger and over here radius of curvature is smaller. So over here, let's say particle is going with constant speed throughout this track. So centripetal acceleration over here will be lesser because radius of curvature is more. So A2 is less than A1 over here. So A2 is always less than A1 because radius of curvature over here is greater than radius of curvature over here. So if you have a picture of the track, I can also think about what the acceleration is going to be. Provided the particle is moving constant speed, I can compare to both the accelerations. All right. So revise pseudo force for today. We're going to apply pseudo force in the next class. Of course, we can solve any problem without pseudo force and with pseudo force. We should be able to do in both the ways. Pseudo force is sometimes easier to crack a problem. It is shorter in length. The solution is shorter in length compared to the solving it without pseudo force. All right. So please revise pseudo force, whatever you know from any book. Any book you have, please revise pseudo force. Just takes 10 minutes to revise and be ready for pseudo force in the next class. Any doubts so far? I can compare these accelerations because my speed is constant throughout and radius of curvature is comparable. I can compare radius of curvature saying radius of curvature 2 is greater than radius of curvature 1. So A2 is less than A1 because A is inversely proportional to radius of curvature. Right? So A is equal to V naught square by R. So A1 is equal to V naught square by R1. A2 is equal to V naught square by R2. Because R1 is less than R2, A1 is greater than A2. All right. Any doubts so far, students? You want me to repeat anything? If you have got no doubts, let's end the session here. In the evening, we'll discuss the further applications of circular motion, dynamics of circular motion, and we'll require pseudo force, application of pseudo force. Again, as I told you, we can solve any problem with and without pseudo force, either from non-inertial frame or inertial frame. But solving it from non-inertial frame is sometimes easier than solving it from inertial reference frame. All right, so please revise pseudo force and come back by evening. It hardly takes 5 to 10 minutes to revise pseudo force. Thank you all, students. Join the next session. You've got next session coming up. You have 2 minutes break. You can take a 2-minute break and join the next session.